So today I will talk about or I will start with a new chapter, that is space-time symmetry and conservation laws. And I will start today's lectures with the introduction to space-time symmetry. So first of all, let me talk about that what is the meaning of space symmetry in space. So let me talk about symmetry in space. Symmetry in space. So first of all, let me talk about its definition. So symmetry in space refers to symmetry in space refers to the property of an object that remains unchanged under certain transformation. Such as there are certain transformations, for example translational transformation, rotational, or reflection, right? So let us first of all try to understand what is translational symmetry. So let me talk about the translational symmetry. Translational symmetry. So an object has translational symmetry if it can be shifted in a certain direction and still looks like same and let us try to understand this with the help of a Python code which I have written. So this is the Python code which I have written. I've just shared it with you and it is on my web page. This is the small code and this is the result of this code. Let me show this to you first of all, that how this code will work. Yeah, say this is the action and this is moving. Say initially this point is here and after some time it will reaches at this point and after that it will reaches at so after a certain distance a it gives its identical replicas. So it is translationally invariant under transformation NA, right? So this I have shown to you here right now. Let me close it. This I have shown it here. Say it is its initial state and after movement across A means when it reaches at this point 2A, then it is again identical copy of this one, and when it is reaches at 3A distance, it is the identical copy of this one, and when it is here, it is the identical copy of this one. So that means it is a translationally invariant. It will be as it is in the initial condition. So that's the meaning of translational symmetry. So next I will talk about that why this in mechanics translational symmetry is more important. So in mechanics, so let me talk about it. This in mechanics, translational symmetry, or sometimes in physics we can generalize it. In mechanics or physics, translational symmetry means invariance of physical law under spatial translation under spatial translation For example, Newton's laws equally apply to objects on Earth or Moon. Means while we talk about the Newton's second law or the first law or the third law, they are equally valid when we are doing for the objects on the Earth or whether on the Moon or in any other planets. So that means they do not depend upon the position. They are independent of that. The physics laws are said to be invariant under spatial translation. But there is a certain problem with the Newtonian laws or the Newton's laws. Means but when objects move with relativistic speeds or strong gravitational field is there, Newton's laws are not valid, right? So I'm just so for the sake of information, but main thing is that regarding this what we call translational symmetry means generally the laws which remain invariant while we are moving from one place to another place, that means they are the translationally invariant or those contains the translational symmetry. And this translational symmetry leads to very important conservation law. Conservation law, that is law of conservation of linear momentum. Conservation of linear momentum. Or in other words, we can say that that law of conservation of linear momentum. I will talk about that later on. That law of conservation of linear momentum is a consequence of translational symmetry. So in the later lectures I will derive that how translational symmetry leads to the conservation of linear momentum. Now let us talk about next symmetry property, that is rotational symmetry. Next is the rotational symmetry. Let me talk about rotational symmetry. So an object has rotational symmetry if it can be rotated. If it can be rotated, if it can be rotated around a fixed point, around a fixed point, and still looks the same, So let us understand it with the help of some Python code which I have written. So it is on my web page also, arunphy.org. Yeah. So let me go to the rotational system. This is a very small code. It's a small code. Let me this is a very small code, and when I run it, it looks like this. Yeah. See, this is a cube and it starts rotating. When it's rotated through 90 degree, say this is our. So when it starts after rotation 90 degree, it looks identical. It looks identical. So that means it is a rotationally invariant. Means it will remain as it is, as it looks before when it's rotated through the 90 degree. So it's a fourfold symmetry element is there in this. So it's a fourfold rotational symmetry. It has the fourfold rotational symmetry, right? So yeah, let me go to the next page. So in physics or in mechanics, rotational symmetry means invariance of physical law. Invariance of physical law under rotation. and it implies that it implies that if a physical system exhibits rotational symmetry, its behavior will be same no matter how it is rotated. No matter how it is rotated. Rotational symmetry leads to conservation of angular momentum This principle is or in other words I can say that rotational symmetry is essential in understanding motion of planets. It's essential in understanding motion of planets, spinning top, and other rotating objects and other rotating objects. Then next comes to be that the reflection symmetry. Next is the reflection symmetry. Next is the reflection symmetry. Yeah. So an object has reflection symmetry if it can be divided into two identical halves by a line of symmetry. I will not talk about it in detail because reflection symmetry is helpful in the quantum mechanics. So say if this is a square and if I cut it like this, or if I cut it into two identical, then they looks identical, right? Or if I cut it this way, then it also looks identical. Or if we place a mirror over here, so this looks identical to this, then we can say that it has the reflection symmetry. And I have written a small code regarding this, and what was that? Let us have a look at that. So this is it like this, yeah. So it is the reflection first of all for the square, yeah. Say these two looks identical. When I remove it, it is not there. And there is another code which I have written for this, what we call for the random phases where line of symmetry is drawn. say here these looks identical for this object, see, but here I couldn't draw any line, but here these are two identical, but I couldn't draw any line for this, but here it is. Let me take, yeah, when I look at this particular diagram, then these two halves are identical. Just a minute, say these are two identical halves. Let me make it little bit slow. Just a minute, yeah. So these are the two identical halves, but here I couldn't draw any such line which will distinguish it, but here I have drawn an identical line, so, and both looks identical, right? Thus is in this way we can look at this what we call reflection symmetry. So now next comes out to be the symmetry in time. Next is a very important concept, that is the symmetry in time. It is a little bit complex concept, and this law suggests that laws of physics should remain the same, whether time moves forward, or backward. Moves forward or backward. This means that, say, some law is valid today and that law is not valid after some, say, 100 years ago or the 100 years later. So that means that law is not valid, because it should be invariant under time translation. So that's all for this introduction to space-time symmetries. And in the next lecture I will talk about the properties of the space and time. So that's all for this lecture.